Let us study the refraction of an obliquely incident ray of light through a parallel-sided glass slab. In such cases, light gets refracted at two interfaces. First, the ray of light is incident on the air-glass interface and refracts through the glass slab. Let the angle of incidence be I and the angle of refraction be R. If the refractive index of glass with respect to air is NGA, then, according to Snell's law, NGA is equal to sin I by sin R. Let this be equation 1. The refracted ray is then incident on the glass-air interface and refracts to air. For glass-to-air refraction, the angle of incidence is equal to R. Let the angle of refraction be theta. If the refractive index of air with respect to glass is NAG, then, according to Snell's law, NAG is equal to sin R by sin theta. But we know that NGA is equal to 1 divided by NAG. On substituting the values of NGA and NAG from equations 1 and 2, and on further simplification, we get angle I is equal to angle theta. This means the emergent ray is parallel to the incident ray, and hence there is no deviation for the incident ray. But note that the light ray has displaced laterally from its original path. The perpendicular distance between the incident ray and the emergent ray is known as lateral shift. The value of lateral shift depends on certain factors like angle of incidence, thickness of the glass slab, refractive index of the medium, and wavelength of the incident ray. Lateral shift increases with an increase in the angle of incidence. Thickness of the glass slab and the refractive index of the medium. Since the refractive index of a medium is inversely proportional to the wavelength of the incident light, lateral shift also is inversely proportional to the wavelength of the incident ray. Let us consider an example. Example 1. A ray of light is incident on a rectangular glass slab of thickness √3 cm at an angle of 45 degrees. If the refractive index of the glass is √2 for the incident light, what is the lateral shift of the emergent light ray? Let PQ be a ray of light ray incident on a glass slab of thickness √3 units. RS represents the emergent ray. QM is the normal to the surface at Q, and PQT represents the path of the incident ray if there were no glass slab. RT represents the lateral shift of the light ray. Given that the angle of incidence I is equal to 45 degrees and the refractive index of the medium is √2. From Snell's law, we have N is equal to sin I by sin R. Substituting the values of N and I, and on further simplification, we get R is equal to 30 degrees. From the triangle QMR, cos R is equal to QM by QR. But QM is the thickness of the glass slab and is equal to √3 units. On substituting these values and on further simplification, we get QR is equal to 2 centimeters. In the triangle QTR, angle TQR is equal to I minus R and is equal to 15 degrees. From the triangle QTR, sin I minus R is equal to TR by QR. TR is equal to QR sin I minus R. On simplification, we find the lateral shift TR is equal to 0.52 centimeter. Now, let us try to reason a common observation that the apparent depth of a transparent material like glass or water when viewed from above is less than the actual depth. Consider a point O at the bottom of a container filled to a depth of h with a liquid of refractive index n. Let OA be a light ray that strikes the liquid-air interface normally and hence travels without any deviation. Consider another light ray, OB, close to OA. Since OB travels from a denser to a rarer medium, it bends away from the normal MM- and forms a ray BC. The ray BC appears to diverge from O'. Then, O' is the image of O and AO' is the apparent depth of the liquid. Say H'. This means when an object in a denser medium is viewed from a rarer medium, the apparent position of the object is closer than its real position due to refraction. Let the angle of incidence OBM be I and the angle of refraction M-BC be R. Since the two angles OBM and AOB are alternate angles, they are equal. Similarly, since the two angles AO'-B and M'-BC are corresponding angles, they are also equal. Then from triangle OAB, tan I is equal to AB by OA, which is equal to AB by H. And from triangle O'-AB, tan R is equal to AB by O'-A and is equal to AB by H'. Therefore, tan I by tan R is equal to AB by H divided by AB by H', which is equal to H' by H. Since the 2 points A and B are close to each other, angles I and R are very small. Hence, tan I and tan R are approximately equal to sin I and sin R. But according to Snell's law, sin I by sin R is equal to 1 by n. Therefore, n is equal to h by h'. Or, the refractive index is equal to real depth by apparent depth. consider the following example. Example 2. A glass slab of thickness 0.30 meter is placed on a table. Find the apparent shift of a point on the table when seen through the glass slab. Assume the refractive index of glass is 3/2. Let P be a point on top of the table and P' be its image when seen through the glass slab. Let the actual depth of point P be h and its apparent depth be h'. Then, the shift in the position of P is h minus h'. We know that the refractive index n of the glass is equal to h by h'. This can also be written as 1 by n is equal to h' by h. On further simplification, we get shift is equal to h into 1 minus 1 by n. Given that h is equal to 0.30 meter and n is equal to 3/2, substituting these values in the above equation and on further simplification, we get the shift as 0.10 meter. Now let us study the effects of atmospheric refraction. The density of atmospheric air is not uniform. It is maximum at the surface of the Earth and decreases with an increase in altitude. Even the refractive index of atmospheric air is maximum at the surface of the Earth and minimum at the outermost layer of the atmosphere. When an oblique light ray from a heavenly body like the Sun enters the atmosphere, it continuously moves into regions of high refractive index and hence bends towards the normal. This bending of light through atmospheric air is known as atmospheric refraction. When the Sun is directly overhead, atmospheric refraction is 0, as the Sun's rays are incident normally. When the Sun is on the horizon, atmospheric refraction is more predominant. This is because when the Sun is on the horizon, light rays have to travel longer distances through the atmosphere. Knowledge of atmospheric refraction is useful in understanding some natural phenomena. The apparent position of any heavenly body is a little above its actual position with respect to an observer on Earth. Observe how the apparent position changes with a change in the actual position of the Sun. When the Sun is just below the horizon, the apparent position is a little above the horizon. Due to this, the Sun is visible about 2 minutes before actual sunrise and 2 minutes after sunset. At the time of sunrise and sunset, the Sun appears to have an oval shape. The rays from the lower region of the Sun travel longer distances than rays from the upper regions. As a result, the upward shift is more for the lower end and the Sun appears oval. The twinkling of stars is also due to atmospheric refraction. Due to winds and other climatic changes, the density of some regions in the atmosphere may change with time. The intensity of light from the stars is low. If these rays happen to pass through regions of the atmosphere with a continuous change of density, then the image of the star changes its location and causes twinkling.